The universe was young, barely 400,000 years old, and everything was changing. For eons before this moment, the cosmos had been a seething furnace, a plasma so hot and dense that nothing could exist as we know it today, just a churning soup of particles colliding endlessly, light trying to escape, but never making it more than a fraction of a distance before slamming into another particle, absorbed, re-emitted, absorbed again, trapped in this cosmic prison of heat and density. But the universe was expanding, cooling, and on this particular day, or rather this particular epoch, since days didn't exist yet, the temperature dropped below a critical threshold, about 3,000 degrees, still unimaginably hot by any standard we know, but cool enough, finally cool enough, for something remarkable to happen. Electrons, which had been zipping around freely, crashing into everything, began to slow down, and protons, the nuclei of hydrogen atoms, were reaching out, pulling these electrons toward them with electromagnetic attraction. And when an electron and proton finally met, finally stuck together, they formed the first hydrogen atom, neutral, stable, and in that moment of binding, a tiny burst of energy was released, a packet of energy that didn't collide with anything nearby because suddenly, with atoms forming everywhere, the universe was becoming transparent, and this packet of energy, this photon, began a journey that would last billions of years. Our photon was born in this moment, released from the formation of a single hydrogen atom somewhere in the early universe, and it began to travel, moving at the only speed it would ever know, the speed of light, 186,000 miles every second, racing through the darkness of the early cosmos, through what we now call the dark ages, a time before stars existed, before galaxies formed, when the universe was just expanding darkness and hydrogen gas, slowly being pulled together by gravity into clumps that would eventually collapse and ignite as the first stars. The photon noticed none of this, because photons don't notice anything. They simply exist and travel. And our photon traveled through this darkness for millions of years, while around it, the universe was transforming, the first stars igniting, massive and blue and burning ferociously, living fast and dying young in supernova explosions that scattered heavier elements into space, and the first black holes forming, small ones from dead stars and larger ones from processes we still don't fully understand, and galaxies beginning to assemble, collections of billions of stars pulled together by gravity, spiraling and colliding and merging. And through all of this, our photon kept moving, undisturbed, unchanged, just traveling in a straight line through expanding space. Billions of years passed, the universe evolved, matured, became filled with structure, galaxy clusters, and superclusters, vast cosmic webs of matter separated by even vaster voids of emptiness, and our photon, now ancient by any reasonable measure, continued its journey, and eventually, after nearly 14 billion years of travel, after crossing distances so vast they're measured in billions of light years, our photon approached a spiral galaxy, unremarkable in most ways, one among hundreds of billions, and within this galaxy was a small yellow star, and orbiting this star was a blue and white planet, and in orbit around this planet was a telescope, and our photon, by pure chance, by the accident of trajectory that began 14 billion years ago, struck the mirror of this telescope, transferred its energy to electrons in the detector, generated an electrical signal that was recorded and processed, and in that instant of absorption our photon ceased to exist, its journey complete. 14 billion years of cosmic history, of stars being born and dying, of galaxies forming and evolving, of planets coalescing from dust, of life emerging and spreading across at least one world. All of this happened during our photons journey, and yet to the photon itself, due to the strange nature of relativity and the speed of light, no time passed at all. The moment of its creation and the moment of its destruction were the same moment, separated by 14 billion years of cosmic time, but zero time in the photon's own experience. If experience is even the right word for something that doesn't have consciousness or awareness or any ability to perceive. But let's step back from this single photon's journey and ask a deeper question. What is light, really? What is this phenomenon that fills the universe, that allows us to see, that carries information across cosmic distances, that somehow behaves as both a wave and a particle, that travels at the universe's ultimate speed limit and experiences no time at all? Light has puzzled humans for as long as we've been able to think about such things. Ancient peoples wondered if light came from our eyes, if we somehow projected vision outward to touch and sense the world, which seems absurd now but made a certain kind of sense if you didn't know better. And over centuries we slowly realized that light must be something external, something that enters our eyes rather than emanating from them, something that can be blocked and reflected and bent. By the time of the scientific revolution, people were studying light carefully, measuring how it behaves when passing through glass or bouncing off mirrors, and one of the key observations was refraction, the way light bends when moving from one medium to another, like from air into water, and this bending could split white light into a rainbow of colors, revealing that white light is actually a mixture of many colors, many wavelengths, and this observation suggested something important about light's nature. Some scientists, looking at how light could be split into colors and how patterns of light and dark could be produced under certain conditions, concluded that light must be a wave, some kind of oscillation traveling through space. And this made sense because waves were everywhere in nature. Water waves on ponds and oceans, sound waves in air, vibrations in solid materials. Waves seemed to be a fundamental way that energy could travel from one place to another without the medium itself having to travel. The water in a pond doesn't flow outward when you throw a stone. It just moves up and down, oscillating. And these oscillations spread outward as ripples, as waves, and maybe light worked the same way, traveling as oscillations in some invisible medium. Other scientists, looking at different observations, concluded that light must be made of tiny particles, little bullets of light streaming from luminous objects and traveling in straight lines until absorbed. And this also made sense because light seemed to travel in straight lines. You could block it with an opaque object and create sharp shadows. And there were other observations that seemed easier to explain if light was made of particles rather than waves. This debate went on for centuries, particle versus wave, and it wasn't until the 1800s that the wave picture seemed to win decisively. Experiments showed clear interference patterns, the way two light sources could combine to create regions of brightness and darkness that only made sense if light was a wave. Waves can interfere with each other. When two wave peaks meet, they add together to create an even bigger peak. When a peak meets a trough, they cancel out, and this interference creates patterns, and light clearly did this, so light must be a wave. But if light is a wave, what's waving? Water waves are oscillations of water. Sound waves are oscillations of air pressure. What medium is oscillating when light travels through empty space, through the vacuum between stars where there's no air, no water, nothing apparent to wave? The answer came from someone studying electricity and magnetism, two phenomena that had seemed separate for most of human history but were slowly being understood as connected. Electric currents could create magnetic fields. Changing magnetic fields could create electric currents. And when someone sat down with the equations describing these relationships and looked at them carefully, looked at what they said about electromagnetic fields in empty space, they discovered something remarkable. If you create a disturbance in an electric field, a ripple, a change, that disturbance doesn't just sit there, it propagates, it travels outward. And as it travels, it creates a disturbance in the magnetic field. And that magnetic disturbance creates another electric disturbance, and they keep regenerating each other, oscillating together, traveling through space as a self-sustaining wave. And when this person calculated how fast these electromagnetic waves would travel, they got a very specific number, right around 186,000 miles per second, exactly the measured speed of light. Light, it turned out, is an electromagnetic wave, oscillations of electric and magnetic fields that regenerate each other and travel through space. And this explained so much, explained why light could travel through vacuum. The vacuum isn't truly empty. It's filled with electromagnetic fields, and explained why light had different colors. Different colors are different wavelengths, different frequencies of oscillation. Red light has long wavelengths, with fields oscillating slowly. Blue light has shorter wavelengths with fields oscillating more rapidly, and this also predicted something new. If light is electromagnetic waves, and there's no inherent limit on wavelength, there must be invisible forms of light, electromagnetic radiation with wavelengths too long or too short for human eyes to detect. Within a few decades, these invisible forms were discovered. First radio waves with wavelengths much longer than visible light, then X-rays with wavelengths much shorter, and then everything in between, microwaves and infrared and ultraviolet and gamma rays, all forms of light, all electromagnetic radiation, differing only in wavelength, in the distance between wave peaks. Your eyes evolved to see a narrow range of wavelengths, the ones most abundant in sunlight and most useful for navigating Earth's surface. But the universe is filled with light across the entire electromagnetic spectrum. Radio waves from pulsars and galaxies, infrared from warm objects and dust clouds, ultraviolet from hot stars, X-rays from matter falling into black holes, gamma rays from the most violent cosmic explosions. All of it is light, all electromagnetic radiation, all following the same fundamental physics. And here's something beautiful about light being electromagnetic. We now understand what causes it, what creates light in the first place. When electrons move, when they accelerate or oscillate or change energy levels, they disturb the electromagnetic field around them, and those disturbances propagate outward as light. When you turn on a light bulb, electrons in the filament or in the gas inside are being jiggled by electric current, moving back and forth rapidly. And every time an electron accelerates, it creates a disturbance in the electromagnetic field, a ripple that spreads outward as light. And when that light reaches your eye, it causes electrons in your retina to jiggle in response. These electrons send signals to your brain, and your brain interprets these signals as vision, as sight, as the world you see. Everything you've ever seen is electrons in your eyes responding to electromagnetic waves created by electrons and other objects. When you look at a tree, you're seeing light that came from the sun, traveled 93 million miles through space, struck electrons and chlorophyll molecules in the tree's leaves, was absorbed and re-emitted with different wavelengths, traveled the short distance from leaf to eye, entered your pupil, passed through your lens, struck your retina, jiggled electrons in photoreceptor cells, generated nerve signals, and all of this happened fast enough that it seems instantaneous. Seems like you're directly perceiving the tree, but really you're perceiving electromagnetic waves that bounced off the tree. You're seeing light, not the tree itself. You only ever see light. And light from distant objects can be very old. The light from the sun is 8 minutes old. It was created in the sun's core through fusion reactions. Took thousands of years to random walk its way to the sun's surface through countless absorptions and re-emissions, and then finally escaped and traveled 8 minutes through space to Earth. So when you look at the sun, you're seeing it as it was 8 minutes ago. And when you look at stars, you're seeing even older light. Light from the nearest star is over 4 years old. Light from more distant stars can be hundreds or thousands or even millions of years old, traveling across space for all that time before finally entering your eye. The night sky is full of ancient light. Every star you see is showing you its past, and the farther you look, the deeper into history you see. And with powerful telescopes, we can see galaxies whose light has been traveling for billions of years. We can see the universe as it was when it was young, can observe how galaxies formed and evolved, can study cosmic history directly through the light that reaches us from those distant times and places. This is one of the profound things about light. It connects you to the universe. When you look at a distant galaxy, you're not just seeing an image. You're receiving actual photons that traveled billions of years to reach your eye. Your eye is interacting with light that left that galaxy in the distant past. There's a direct physical connection between your retina and that ancient galaxy, mediated by light, by photons that crossed intergalactic space to bring you information about distant places and times. And light carries information. The wavelength tells you about temperature and composition. Hot objects emit shorter wavelengths. Cooler objects emit longer wavelengths. And when light passes through gas, some wavelengths get absorbed by atoms in the gas, creating dark lines in the spectrum, and different elements absorb different wavelengths in unique patterns. So by analyzing which wavelengths are present or missing, we can determine what distant objects are made of, how hot they are, how fast they're moving toward or away from us, whether they have planets orbiting them, all from light, from analyzing the electromagnetic radiation that reaches us. Everything we know about the universe beyond Earth, we learn from light. We can't travel to distant stars or other galaxies, at least not with any technology we currently have or are likely to develop soon. But we don't need to travel there because light travels from there to here, carrying information, and we've learned to decode that information, to extract from light's wavelengths and polarization, and timing everything we need to know about distant cosmic objects and events. But here's where things get strange. Where the wave picture of light, as elegant and successful as it is, starts to show cracks, starts to reveal that something deeper is going on. When light interacts with matter, when photons are absorbed by atoms or emitted by atoms, the energy doesn't flow continuously like you'd expect from a wave. Instead, energy is exchanged in discrete packets. In quanta, an atom can absorb a photon and gain a specific amount of energy all at once. Or an atom can emit a photon and lose a specific amount of energy instantaneously, and the amount of energy depends on the light's frequency. Blue light photons carry more energy than red light photons, ultraviolet even more. X-rays and gamma rays carry enormous amounts of energy per photon, and this quantized behavior, this exchange of energy in discrete lumps rather than continuous flow, suggests that light isn't just a wave but also has particle-like properties. Scientists discovered this by studying what happens when light hits certain metals. They found that blue light could knock electrons out of the metal, while red light could not. Regardless of intensity, you could shine dim blue light and electrons would be emitted immediately. Or you could shine bright red light and no electrons would come out no matter how long you waited. And this only makes sense if light delivers energy in packets, in photons. Blue photons have enough energy to kick an electron free. Red photons don't, and intensity just means more photons, not more energy per photon. So bright red light is just lots of low-energy photons that individually can't free an electron. This was confusing because light clearly behaves as a wave in many situations, showing interference and diffraction, but also clearly behaves as a particle in other situations, delivering energy in discrete packets. And the resolution to this confusion is one of the deepest insights of quantum mechanics. Light is neither purely a wave nor purely a particle. It's something else, something that has properties of both depending on how you look at it, how you measure it. When light is traveling through space, it behaves like a wave. It can interfere with itself, can bend around obstacles, can show all the characteristic wave behaviors. But when light interacts with matter, when it's absorbed or emitted, it behaves like a particle, like a photon, transferring energy all at once in a discrete quantum. And both descriptions are correct. Both are necessary to fully understand light's behavior. Light is fundamentally a quantum object, and quantum objects don't fit neatly into our classical categories of wave or particle. They're something else, something that exhibits both properties depending on circumstances. And it's not just light. Everything in the quantum world has this dual nature. Electrons act like particles when you measure their position, but act like waves when you look at their motion. Even large molecules have been shown to exhibit wave-like interference patterns under the right conditions. The quantum world is genuinely strange, stranger than our everyday intuition can easily grasp. But it's the way the universe actually works at fundamental scales. So light is a quantum electromagnetic wave-particle thing, and the universe is filled with it. Photons traveling in every direction from every luminous object, most of them never hitting anything, just traveling forever through empty space. But some of them, by chance, by the geometry of emission and the vastness of space, strike matter, get absorbed, transfer their energy, cease to exist as photons, and in that absorption they might cause an electron in an atom to jump to a higher energy level, or they might warm an object slightly, or they might trigger a chemical reaction, or they might enter an eye and create the sensation of sight, or they might strike a telescope detector and be recorded for scientific analysis. Your entire visual experience of the world, everything you see, is light being absorbed by cells in your retina, photons ending their journeys in your eyes, transferring their energy to molecules that then send signals to your brain, and your brain constructs from these signals the rich, detailed, colorful experience of vision. The world as you perceive it, and it happens so automatically, so seamlessly, that you never think about it. never consider that seeing is actually detecting electromagnetic radiation. That vision is your brain interpreting signals from photons absorbed by your retinas. And those photons came from somewhere. Some of them came from the sun, traveled millions of miles, bounced off objects around you, entered your eyes. Some came from artificial lights, electrons being jiggled by electric currents, creating photons that traveled short distances to your eyes. And if you look at stars at night, some of those photons have been traveling for years or centuries or millennia. Ancient light from distant suns, and all of it ends in your eyes, absorbed, converted to neural signals, experienced as sight. There's something profound about this, about being connected to the universe through light. When you watch a sunset, you're seeing photons that left the sun 8 minutes ago. When you look at the moon, you're seeing reflected sunlight that's about a second old. When you look at stars, you're seeing light that's years or centuries old. When you look at distant galaxies through a telescope, you're seeing light that's millions or billions of years old. You're looking back in time, seeing the universe as it was. And all of this is possible because light travels, because photons can cross vast distances carrying information, carrying energy, connecting distant parts of the cosmos. And light moves fast, faster than anything else in the universe. Nothing can exceed light speed. It's the cosmic speed limit built into the structure of space-time itself. And this speed limit has profound consequences. It means there's a maximum rate at which information can travel, which means there's a fundamental limit to how quickly distant parts of the universe can influence each other. It means that causality has a speed. Cause and effect can't happen instantaneously across distance. Effects propagate outward at light speed, no faster. This speed limit is also why light experiences time strangely. At light speed, according to relativity, time stops, distances shrink to zero. So from a photon's perspective, if photons could have perspectives, the moment of emission and the moment of absorption are the same moment. No time passes. The distance traveled is zero. The entire journey, whether it's 8 minutes from the sun or 14 billion years from the early universe, happens in an instant of zero duration, which seems impossible from our perspective. But that's what the mathematics of relativity tells us, and relativity has been tested extensively and confirmed to incredible precision. So we know this is correct, even if it's deeply counterintuitive. Our photon that we followed at the beginning, the one born in the early universe and absorbed by a telescope 14 billion years later, experienced none of that journey, didn't see the dark ages or the first stars or the formation of galaxies or the birth of the solar system or the evolution of life on Earth, noticed nothing because to the photon no time passed. It existed in a single moment that stretched across 14 billion years of cosmic history, but was experienced as an instant, and then it was absorbed and ceased to exist. And in its absorption, it transferred information about the early universe to our detectors, gave us a glimpse of conditions hundreds of thousands of years after the Big Bang. And this information, carried across cosmic time and distance by a single photon, helps us understand where the universe came from and how it evolved. Light is everywhere, connecting everything. Most of the universe's volume is empty space, vacuum, but even the vacuum is crossed by light, by photons traveling from distant sources, and in regions near stars or galaxies there are floods of photons, enormous numbers of them streaming in all directions, some emitted recently, some traveling for millions or billions of years, all moving at the same speed, all potentially carrying information about their sources. And light doesn't just travel through empty space. It can interact with matter along the way, can be scattered by dust, absorbed and re-emitted, bent by gravity when passing near massive objects. And these interactions tell us about what's in space. Even when we can't see it directly, we can detect dust clouds by how they dim and redden starlight passing through them, can detect black holes by how they bend light from background sources, can even detect dark matter which doesn't emit or absorb light at all, by observing how it gravitationally lenses light from distant galaxies. Gravity bending light is one of the predictions of relativity, mass and energy curve space-time, and light follows the curvature, so light paths bend near massive objects, and this has been confirmed countless times. We see it when looking at images of distant galaxies. Often they appear stretched and distorted, and sometimes multiply imaged, all because their light passed near a massive galaxy cluster between them and us, and the cluster's gravity bent the light paths, creating these distortions, and by analyzing the distortions we can map the mass distribution in the cluster, can see where dark matter is concentrated even though dark matter itself is invisible. Light is our window to the universe. Everything we observe beyond Earth, we observe through light, and we've built instruments to observe light across the entire electromagnetic spectrum. Radio telescopes picking up long wavelength radiation from cold gas and energetic cosmic events. Infrared telescopes seeing through dust clouds to observe star formation and distant galaxies. Visible light telescopes capturing the colors we can see with our eyes. Ultraviolet telescopes studying hot stars and energetic processes. X-ray and gamma-ray telescopes observing the most extreme events. Black holes accreting matter, neutron stars colliding, supernova exploding. Each wavelength tells us something different, shows us different aspects of the universe. Radio waves reveal cold molecular clouds where stars form. Infrared shows us warm dust and distant galaxies whose light has been redshifted by cosmic expansion. Visible light shows us stars and galaxies as they are or were. Ultraviolet reveals hot young stars and energetic regions. X-rays and gamma rays show us the universe's most violent phenomena. And by observing across all these wavelengths, we build up a complete picture, understanding the universe in all its complexity. And the universe is constantly creating new light. Every fusion reaction in every star's core ultimately produces photons. Every time an electron drops to a lower energy level, a photon is emitted. Every time matter accelerates, photons are created. The universe is a light-generating machine, constantly producing photons across all wavelengths, and most of these photons will travel forever, never hitting anything, just propagating outward through expanding space. But some will be absorbed, will interact with matter, will transfer their energy and information, and cease to exist as photons. The cosmic microwave background, that ancient light from the early universe that we can still detect today, is everywhere, flooding all of space. Photons from when the universe first became transparent, and they've been traveling ever since, cooled by cosmic expansion from visible light to microwave wavelengths, but still there, still carrying information about the early universe. And by mapping these photons, by measuring tiny variations in their temperature across the sky, we've learned enormous amounts about cosmic history, about the universe's age and composition and evolution. Those photons, like the one we followed at the beginning, were created when electrons and protons first combined to form neutral atoms. And they've been traveling for nearly 14 billion years, and they're still arriving, still flooding through space. And we can detect them, can study them, can learn from them, and this ancient light connects us directly to the early universe. Lets us observe conditions from hundreds of thousands of years after the Big Bang, which is remarkable when you think about it. We can see the baby universe, can observe it directly through light that has been traveling all this time. Light makes the universe observable. Without light, we'd know almost nothing about anything beyond Earth's surface. We'd be blind to the cosmos. But because stars emit light, because galaxies glow, because even the vacuum of space is crossed by photons from distant sources, we can observe, can study, can understand, and every time you look up at the night sky, every time you see stars twinkling, you're participating in this ancient connection. You're receiving photons that traveled light years or centuries or millennia to reach your eyes, ancient travelers ending their journeys by creating the experience of sight in your mind. The universe is showing itself to you through light, and you, standing on Earth's surface, looking up, are receiving that light, are part of this cosmic web of electromagnetic radiation connecting everything. And that's beautiful, that's profound, that makes you part of something vast and ancient and ongoing. You're not separate from the cosmos, you're embedded in it, connected to distant stars and galaxies through the light they send, through photons that cross space to reach you. And every day, every moment, light surrounds you. Photons from the sun illuminating your world. Photons from artificial lights letting you see at night. Photons from screens carrying information and entertainment. Photons from every visible object entering your eyes and creating your visual experience. It's so constant, so ubiquitous, that you take it completely for granted. But light is extraordinary, as quantum electromagnetic radiation propagating through space at the universe's speed limit is how stars tell you they exist, how the early universe shows you its face, how anything visible makes itself known. Tomorrow the sun will rise again, will flood your part of Earth with light, 8-minute-old photons from a star 93 million miles away, and you'll see the world around you and probably won't think about the fact that seeing requires light, requires photons entering your eyes and being absorbed by your retinas. But it does. Vision is photon detection, and those photons traveled from their sources to your eyes at incredible speed, crossed distance in essentially no time from their own perspective, and ended their existence by giving you sight. Light is one of the fundamental phenomena of the universe, is how electromagnetic force manifests over distance, is how energy and information travel through space, is what lets us see and observe and understand the cosmos. And it's everywhere, always connecting everything. And now, understanding this, you can never look at light quite the same way again, can never see a sunbeam or a starlit sky without knowing what you're really seeing, without recognizing that you're observing quantum electromagnetic radiation, ancient photons ending their journeys in your eyes, the universe showing itself to you through light. Rest with this understanding. Let it settle. Let yourself feel connected to the cosmos through this fundamental phenomenon, through light that surrounds you always, that makes vision possible, that carries information across vast distances, that connects you to stars and galaxies and the ancient universe itself, all through photons, through light, through the electromagnetic radiation that fills the cosmos and makes it knowable, makes it beautiful, makes it yours to observe and wonder at and understand. Light surrounds us constantly, but there are places in the universe where light cannot exist, places where even photons, traveling at the ultimate cosmic speed, cannot escape, and these places reveal something profound about the nature of light itself and about the fabric of space and time. Black holes are regions where gravity becomes so intense that space-time itself is curved to an extreme degree, bent so severely that nothing, not even light, can escape once it crosses a boundary we call the event horizon. And this boundary is not a physical surface, not a wall or barrier, but simply a point of no return, a location where the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses this boundary can ever come back out. Imagine standing near a black hole, not too close but close enough to observe its effects, and imagine shining a flashlight toward it. The photons from your flashlight would travel toward the black hole, and some of them would miss and continue past into space, but others would get close enough to be affected by the black hole's gravity. Their paths would curve, bend toward the black hole, and some photons would spiral around the black hole multiple times before either escaping or falling in, and photons that crossed the event horizon would fall inward, would be pulled inexorably toward the singularity at the center, and from outside the event horizon you would see nothing. The black hole would appear as a dark sphere, a region of absolute blackness surrounded by distorted images of background stars, their light bent around the black hole by its gravity. This bending of light by gravity is one of the key predictions of general relativity, Einstein's theory that describes gravity not as a force but as the curvature of space-time. Mass and energy curve space-time, and objects moving through curved space-time follow curved paths, and this applies to light just as much as to matter. Photons follow geodesics, the straightest possible paths through curved space-time, but when space-time is curved, these paths are themselves curved, so light bends around massive objects. We see this effect throughout the universe. Massive galaxy clusters act as gravitational lenses, bending light from more distant galaxies, and this bending can magnify distant galaxies, making them appear larger and brighter than they would otherwise, and it can create multiple images of the same galaxy, and it can stretch galaxies into long arcs. And by analyzing these distortions, we can map the mass distribution in the lensing cluster, can determine where dark matter is concentrated, because dark matter, which doesn't emit or absorb light, still has mass, still curves space-time, still affects the paths of photons passing nearby. The most extreme lensing occurs near black holes, where space-time curvature is most severe. And if you could somehow survive near a black hole's event horizon and look around, you would see strange and distorted views. You might see multiple images of the same distant star, light from that star taking different paths around the black hole to reach your eyes, and you might see stars that are actually behind the black hole appearing above or below it, their light bent around by gravity. And if the black hole is accreting matter, if there's a disk of gas and dust spiraling inward, you would see that disk appear both above and below the black hole simultaneously. Light from the far side of the disk bent over and under the black hole to reach you, creating a bizarre doubled image. But the strangest thing about being near a black hole would be the effect on time itself, because gravity doesn't just curve space, it also affects time. In strong gravitational fields, time passes more slowly relative to regions of weaker gravity. And this has been measured, has been confirmed by comparing atomic clocks at different altitudes on Earth. Clocks at sea level, deeper in Earth's gravitational well, tick slightly slower than clocks on mountaintops. The difference is tiny, measured in billionths of a second, but it's real, it's measurable, and this effect becomes dramatic near black holes. If you watched someone fall toward a black hole from a safe distance away, you would see them slow down as they approach the event horizon, their motion becoming more and more sluggish, asymptotically approaching the horizon, but never quite reaching it in your reference frame, and you would see their light red shifted to longer wavelengths by the gravitational field. They would appear to fade and redden as they approached the horizon, eventually becoming invisible as their light was red shifted beyond detection. But from their perspective, from the perspective of the falling person, nothing special happens at the event horizon. They would cross it smoothly, wouldn't notice any particular moment of crossing, though they would notice the increasing tidal forces, the difference in gravitational pull between their head and feet becoming stronger and stronger until eventually, as they approached the singularity, these tidal forces would tear them apart, would stretch them like taffy in a process astronomers somewhat grimly call spaghettification. This difference in perspectives, this disagreement about what happens and when, is one of the strange consequences of relativity. Different observers in different reference frames see different things. Both perspectives are valid. Both are correct descriptions of reality from their particular point of view, and neither perspective is more true than the other. They're just different ways of slicing up space-time, different ways of dividing events into space and time. And for light itself, for photons, the experience is even stranger. Photons travel at light speed, which means that from the photon's perspective, time doesn't pass at all. Distances are contracted to zero. The entire journey from emission to absorption happens in a single instant of zero duration, and this is true whether the photon travels a few feet or across the entire universe, whether it exists for a nanosecond or for billions of years. From its own perspective, if such a thing can be said to exist, the journey is instantaneous. This means photons don't experience anything, don't have a history, don't age or change during their journey. They simply exist at the moment of emission and at the moment of absorption, and these are the same moment from the photon's perspective. And everything that happens between, all the distance traveled, all the time that passes in other reference frames is compressed to nothing in the photon's frame. There's something almost poetic about this, about light connecting distant parts of the universe across vast gulfs of space and time, but experiencing none of that journey itself. Photons are messengers that don't experience the message, carriers of information that exist outside of time in a certain sense, or at the boundary of time, moving so fast that time stops for them, connecting events across space and across time, but themselves existing in a timeless state. And this connects to one of the deep mysteries about light, about how photons are created and absorbed, about how they connect emitter and absorber across space and time, because in quantum mechanics, the description of a photon being emitted by one electron and later absorbed by another. Electron is not quite as simple as it seems. It's not that one electron randomly emits a photon that then travels through space, hoping to find another electron to absorb it. Instead, the emission and absorption are connected, are part of a single quantum event, and some interpretations of quantum mechanics suggest that in a certain sense the emitting and absorbing electrons communicate, agree on the exchange of the photon, and this agreement somehow happens across time. The electron in the past that emits and the electron in the future that absorbs both participate in creating the photon's journey. This sounds bizarre. Sounds like backwards in time communication, but it's consistent with the mathematics of quantum mechanics, which doesn't distinguish between past and future in the way classical physics does. Quantum mechanics treats time symmetrically in many ways, and the idea that emission and absorption are connected, that they're two ends of a single event rather than separate events connected by a photon's journey, resolves certain puzzles about how photons work. And this means that when you look at a distant star, when a photon from that star enters your eye, there's a sense in which an electron in the star's atmosphere and an electron in your retina have reached across light years of space and years of time to exchange that photon, have agreed to this exchange, and the photon's journey is the manifestation of that agreement, the physical connection between two events separated in space and time, but connected through the exchange of light. This is one of many strange aspects of quantum mechanics, this blurring of the distinction between past and future, this entanglement of distant events, but it's the way the universe works at fundamental levels, and light, being a quantum phenomenon, exhibits this strangeness fully. And light isn't just photons traveling through empty space. Light can also be trapped, can be contained and manipulated and used. When light enters a medium like glass or water, it slows down, not because the photons themselves slow down, but because the light is constantly being absorbed and re-emitted by atoms in the material. And this process of absorption and re-emission takes time, so the effective speed of light through the material is lower than light speed in vacuum, and different wavelengths slow down by different amounts, which is why prisms can split white light into a rainbow. Blue light slows more than red light in glass, so blue bends more when entering or leaving the prism, and this separates the colors. And light can be reflected, can bounce off surfaces, and the smoothness of the surface determines whether the reflection is clear or diffuse. A perfectly smooth mirror reflects light in an organized way, maintaining the image, while a rough surface scatters light in random directions, destroying any image but still reflecting the light. And this is why most objects are visible. They reflect light. Light from the sun or from artificial sources strikes objects, and some of it is absorbed, but some is reflected. And the reflected light carries information about the object's color and texture and shape. And this reflected light can enter your eye and create vision. Color itself as a property of light is determined by wavelength or frequency, and different wavelengths are perceived as different colors. Red light has wavelengths around 700 nanometers, blue light around 400 nanometers, and in between are all the other colors of the visible spectrum, orange and yellow and green. And these wavelengths are tiny, hundreds of thousands of waves fit in a single millimeter, and yet our eyes can distinguish between different wavelengths quite well, can perceive the difference between red and orange, between blue and cyan, because we have different types of color-sensitive cells in our retinas, cells that respond preferentially to different wavelengths, and our brains compare the responses of these different cell types to determine color. But color is also subjective in a sense, is a construction of our nervous system. The photons themselves don't have color, they have wavelength, and different organisms with different types of photoreceptors perceive colors differently. Some animals can see ultraviolet light that's invisible to us, can perceive wavelengths shorter than 400 nanometers, and some can see infrared, can perceive longer wavelengths, and their experience of the world must be quite different from ours. They're seeing light we can't see, perceiving colors we can't perceive, and this reminds us that our senses show us a limited slice of reality. There's more to the universe than we can directly perceive, but we've built instruments to extend our senses, to detect light across all wavelengths, to show us the universe in its full electromagnetic glory. And the universe produces light through many processes. Stars produce light through fusion, through nuclear reactions in their cores that release energy, and this energy works its way to the surface and is radiated into space as light, mostly visible light for stars like the Sun, but also ultraviolet and infrared and other wavelengths. And the spectrum of light a star emits tells us about its temperature. Hot stars emit more blue and ultraviolet light, cooler stars emit more red and infrared, and by analyzing a star's spectrum, we can determine its temperature and composition and many other properties. When matter falls into a black hole, it heats up through friction and compression, and this hot matter emits X-rays, high-energy photons, and these X-rays can escape the region around the black hole, can travel through space, and reach our X-ray telescopes. And this is how we detect many black holes. Not by seeing the black hole itself, which emits no light, but by seeing the X-rays from hot matter falling into it. The accretion disk glowing brilliantly in X-rays just outside the event horizon. Supernova, the explosive death of massive stars, produce light across all wavelengths. A supernova can briefly outshine an entire galaxy, can emit as much light in a few weeks as the Sun will emit in its entire 10 billion year lifetime. And this light comes from the shock wave heating the star's outer layers as they're blown into space, and from radioactive decay of elements created in the explosion, and supernova light can be seen across enormous distances, can be detected in galaxies hundreds of millions or billions of light years away. And by studying supernova in distant galaxies, we've learned that the universe's expansion is accelerating, that some mysterious dark energy is pushing galaxies apart at an ever-increasing rate. And there's light from the earliest universe, the cosmic microwave background, photons that have been traveling since the universe first became transparent, and these photons have been stretched by cosmic expansion, redshifted from visible light to microwave wavelengths, but they're still there, still arriving, still carrying information about conditions in the early universe. And by mapping tiny variations in the temperature of this cosmic background, we've learned about the universe's age and composition and geometry, have confirmed that the universe is about 13.8 billion years old, is spatially flat, or very nearly so, is composed mostly of dark energy and dark matter, with ordinary matter making up only about 5% of the total. This ancient light, these cosmic microwave photons, are everywhere, flooding through space in all directions. You're being bombarded by them constantly. They're passing through your body right now, though you can't see or feel them because your eyes don't detect microwave wavelengths, and because each individual photon carries very little energy. But they're there, ancient light from the baby universe, photons that have been traveling longer than any others, and they connect you directly to the Big Bang, to the earliest moments of cosmic history. And light from distant galaxies is redshifted by cosmic expansion, The expansion of space stretches the wavelengths of photons traveling through it, so light from very distant galaxies is shifted toward red and infrared wavelengths, and the amount of redshift tells us how far away the galaxy is and how fast it's receding due to cosmic expansion. And by measuring redshifts of many galaxies, we can map the universe's large-scale structure, can see how galaxies cluster and how these clusters are arranged in vast filaments and walls surrounding even vaster voids. The universe is transparent to most wavelengths of light. Photons can travel across cosmic distances without being absorbed, which is fortunate because otherwise we couldn't observe distant galaxies, couldn't see the cosmic microwave background, couldn't study the universe's history. But there are some wavelengths that don't travel well through space. Very low energy radio waves can be scattered by the thin plasma in intergalactic space, and very high energy gamma rays can interact with starlight and cosmic microwave background photons, creating particle-antiparticle pairs and losing energy. So there are limits to how far we can see at certain wavelengths. But across most of the spectrum, the universe is beautifully transparent. And this transparency means that light can carry information across vast distances with minimal loss. A photon emitted by a star in a galaxy billions of light years away can travel all that distance and arrive at Earth essentially unchanged, still carrying the same wavelength, the same energy it had when emitted, though stretched by cosmic expansion. And when we detect that photon, we're receiving information directly from that distant star, unmediated, unchanged, pure information about conditions billions of years ago, billions of light years away. There's something remarkable about this, about the fact that the universe is transparent, that light can travel freely, that information can cross cosmic distances, because it means the universe is knowable, is observable. We're not trapped in a local bubble, unable to see beyond our immediate neighborhood. Instead, we can observe galaxies across billions of light years, can see almost to the edge of the observable universe, can study cosmic history from the earliest moments to the present, all because light travels freely and carries information faithfully across space and time. And we've built instruments to detect light across all wavelengths. Radio telescopes with enormous dishes collecting faint radio waves from distant galaxies and pulsars. Infrared telescopes cooled to extremely low temperatures to detect the faint heat from distant galaxies and forming stars. Optical telescopes with huge mirrors gathering visible light. Ultraviolet telescopes in space above Earth's atmosphere, which absorbs most ultraviolet light. X-ray and gamma-ray telescopes detecting the highest energy photons from the most violent cosmic events. And each type of telescope shows us different aspects of the universe, reveals different phenomena, and together they give us a comprehensive view, show us the universe in all its complexity and beauty. The James Webb Space Telescope, launched recently, is observing in infrared wavelengths, and it's seeing galaxies so distant their light has been traveling for over 13 billion years, seeing the universe as it was when it was very young, when the first galaxies were just forming. And these observations are revealing how structure emerged in the early universe, how the first stars and galaxies formed from the nearly uniform distribution of matter that existed shortly after the Big Bang. And this is possible because light from those early galaxies has been traveling all this time, carrying information about the early universe. And we can receive that light, can analyze it, can learn from it. And light doesn't just travel through space, it can be stored, can be trapped in reflective cavities or in optical fibers, can be manipulated and controlled. We use light to transmit information through fiber optic cables, sending pulses of light carrying digital data across vast distances at nearly light speed. And we use lasers, concentrated beams of coherent light, for everything from cutting metal to performing surgery to measuring distances with incredible precision. And we're learning to manipulate light at quantum levels to create single photons on demand, to entangle photons so they share quantum states even when separated by large distances. And these technologies may lead to quantum computers and quantum communication networks, new ways of processing and transmitting information that take advantage of light's quantum properties. Light is also how stars tell us they exist, how they make their presence known across the void. Without light, we'd have no way to detect distant stars. They'd be invisible, unknown. But because they emit light, because photons stream from their surfaces in all directions, we can see them, can study them, can learn about their properties and their evolution. And this is true for galaxies as well. Galaxies emit light, the combined light of billions of stars, and this light can be seen across enormous distances, allowing us to map the universe's structure, to see how galaxies are distributed, how they cluster and evolve. And there are objects that emit light in specific wavelengths. Pulsars emit beams of radio waves that sweep across space like lighthouse beams as the pulsar rotates. And when these beams point toward Earth, we detect regular pulses, incredibly regular, more regular than any human-made clock. And these pulses tell us about the pulsar's rotation rate and magnetic field and other properties. And quasars, extremely bright galactic centers powered by supermassive black holes accreting matter, emit enormous amounts of light across all wavelengths and can be seen across most of the observable universe. And by studying quasars at different distances, we can trace how galaxies and black holes evolved over cosmic history. Every luminous object in the universe is telling its story through light, through the photons it emits, and we're learning to read these stories, to extract from light's wavelengths and intensities and polarization and timing all the information we need to understand distant objects. And this is one of humanity's great achievements, learning to decode light, to understand what it tells us, to use it as a tool for understanding the cosmos. And light connects you personally to the universe. Every time you look at the night sky, you're receiving photons that traveled light years to reach you, ancient light from distant suns. And these photons are ending their journeys in your eyes, transferring their energy to molecules in your retina, generating nerve signals that your brain interprets as the experience of seeing stars. And in that moment of absorption and that transfer of energy from photon to molecule, you're connected directly to those distant stars. You're participating in a physical interaction with light that left those stars years or decades or centuries ago. This connection is real, is physical, is mediated by actual photons crossing actual space. It's not metaphorical or poetic, though it is both of those things as well, but it's fundamentally a physical connection. Electromagnetic radiation emitted by atoms and distant stars and absorbed by atoms in your eyes. And this connection makes you part of the cosmos, makes you a participant in the universe's light-filled web of interactions. And during the day, you're connected to the sun in the same way. Every moment of daylight involves photons from the sun entering your eyes, 8-minute-old light from a star 93 million miles away. And these photons illuminate your world, make vision possible. and also warm your skin, provide the energy that drives Earth's weather and ocean currents, power photosynthesis in plants, which produce the oxygen you breathe and the food you eat. The sun's light is fundamental to almost everything about life on Earth, and every photon arriving from the sun is an 8-minute-old messenger carrying energy across the solar system. Light is also how we communicate, how we send signals. Radio waves carry broadcasts and cell phone calls and Wi-Fi data. Infrared remotes control devices. Fiber optic cables carry internet traffic as pulses of light. Even in space, we communicate using light, sending radio signals to spacecraft across the solar system. And these signals travel at light speed, which means there's always a delay, several minutes to Mars, hours to the outer planets. And this delay is a fundamental consequence of light's finite speed. Information cannot travel faster than light. So communication across space always involves waiting for light speed signals to propagate. And light is how we measure distances in astronomy. We can't lay a ruler across space to measure how far away a star is, but we can use light, can observe how bright a star appears, and compare it to how bright it actually is, and calculate the distance. Or we can measure how long light takes to travel, can bounce laser beams off the moon and measure the round-trip time, and calculate the moon's distance with incredible precision. Currently, we know the moon's distance to within millimeters using this technique, measuring how long light takes to make the journey there and back. Light is fast, but space is vast, and this combination means that light takes time to cross cosmic distances, 8 minutes from the sun, 4 years from the nearest star, millions or billions of years from distant galaxies. And this light-traveled time means we're always seeing the past, never the present. The light you see from any distant object left that object in the past, and the farther away the object, the older the light. So looking into space is looking back in time, and this makes astronomy unique among sciences. Astronomers can directly observe the past, can see how the universe looked billions of years ago by observing very distant galaxies, can trace cosmic history by looking at objects at different distances. No other science can do this. Historians study records and artifacts from the past, but can't directly observe historical events. But astronomers can literally see the past by observing distant light, can watch galaxies as they were billions of years ago, can study the evolution of cosmic structure over time. And this is all possible because light travels at finite speed and takes time to cross space. The speed of light is both a limit and a tool, a constraint and an opportunity. And thinking about light, about its properties and behavior, about how it connects distant parts of the universe, about how it makes the cosmos observable and understandable, there's a sense of wonder that emerges, a recognition that light is not just a phenomenon to be studied, but a profound feature of reality, something that connects everything, that makes vision and understanding possible, that carries energy and information across vast distances, that experiences no time despite traveling for eons. Light is everywhere, always surrounding you, passing through you, connecting you to the sun and stars and the ancient universe. And now understanding what light is, understanding that it's quantum electromagnetic radiation traveling at the universe's speed limit, understanding that every photon connects emitter and absorber across space and time, understanding that vision is photon detection, and that seeing is receiving light from your surroundings, Understanding all this, you can appreciate light in a new way, can recognize its fundamental importance, its ubiquity, its role in making the universe knowable. Tomorrow, when the sun rises, when light floods your environment, when you open your eyes and see the world, remember that you're detecting photons. That vision is electromagnetic radiation being absorbed by your retinas. That the light you see left the sun 8 minutes ago and traveled 93 million miles to reach you. Remember that when you look at stars, you're seeing ancient light that's been traveling for years or centuries. Remember that you're connected to the cosmos through light, through photons that cross space to bring you information about distant places and times. Light makes the universe visible, makes it knowable, makes it beautiful, and you, with your eyes that detect light, with your brain that interprets electromagnetic signals, you're part of this light-filled cosmos. You're a light detector, a photon absorber, a participant in the universe's electromagnetic web. And that's remarkable. That makes you part of something vast and ancient and ongoing, something that connects all luminous objects across all of space. And light is the medium of connection, the carrier of information, the messenger that travels from stars to eyes, from galaxies to telescopes, from the early universe to the present moment. Sleep now, rest, let these thoughts about light settle. Let yourself feel connected to the universe through this fundamental phenomenon, through electromagnetic radiation that fills space and makes observation possible, through photons that connect you to distant stars and ancient times, through light that surrounds you always, that makes seeing possible, that carries the universe's message to your eyes. Light that is both wave and particle, both energy and information, both quantum phenomenon and classical wave. Light that travels at the ultimate speed and experiences no time. Light that bends around massive objects and carries information across cosmic distances. Light that makes the universe beautiful and knowable and connected. All of it, all of this is light, is photons, is electromagnetic radiation, and it's everywhere, always connecting everything. And now you know. Now you understand, and the universe is showing itself to you through light, through ancient photons, ending their journeys in your eyes. And that's extraordinary, that's beautiful, that makes you part of everything. The universe glows, shines, radiates light in all directions, from all luminous sources. And this light crosses space, carries information, creates connections, makes observation possible, and you, seeing this light, receiving these photons, you're participating in this cosmic dance of electromagnetic radiation. You're connected to everything through light, and that connection is real, is physical, is profound, and it's there every moment of every day. Light surrounding you, connecting you to the cosmos, making the universe yours to observe and wonder at and understand, all through light, through photons, through electromagnetic waves that travel from sources to observers and create in that journey the possibility of vision, of knowledge, of connection, of understanding. And the universe is vast and ancient and filled with light, and you're part of it, connected through light to everything that shines, everything that glows, everything that emits electromagnetic radiation across the cosmos. And that's beautiful, that's profound, that makes you part of something infinite and eternal and magnificent, all through light, all through photons, all through the electromagnetic radiation that fills the universe and makes it knowable and beautiful and connected. Good night.